Hello and welcome. Happy Monday. We're back in the grind. Hope everybody had a good weekend. Staying home, having fun. I'm going to try to figure out how to make the font on Wireshark bigger before we get started, and I am using the VM in Solidarity. If you have the option to use something else, so if you're comfortable installing Wireshark on your own computer, I recommend you do so because it will be a lot faster. The VM is very slow. We'll see if I can even pull this off on the VM, but just in solidarity with those of you who want to use the VM, I'm using it. So I'm able to, let's have a look. We'll just get started and see if it's the right size. So here I am in VM land. I've just started Wireshark. The version on the VM is slightly older, so if you've installed your own, it'll look a little bit different. I'll try to point out the differences that I can remember as we go, but really Wireshark's interface hasn't changed much in many years. Sometimes as conventions on what we call things change, Wireshark will update those. We'll see that in this lab actually. That the convention for naming something has changed. So let's pop into the lab document real quick. Actually, before we do that, let's look at where we left off last week. When we left off last week, we were talking about switches. We had just talked about how a switch was basically a deaf mute on the network. A switch didn't have any address of its own. It didn't perform ARP, and that it figured out who was connected to which port by just snooping the incoming traffic there and looking at the sender field. And we talked about how if it doesn't have a particular destination in its switch table, it will just forward it to everybody, and then eventually it will figure out who is at every port just based on the replies and that sort of thing. And then we didn't cover the advantages of switching, but again, it's not that relevant anymore because the star topology has become dominant and the bus topologies are no longer a thing, so collisions are no longer a thing. We don't have multiple links sharing the same cable anymore. Back when we did have multiple links sharing the same cable, one busted NIC could kill the whole network because it would just shout nonsense into the cable and that would ruin everybody's signal. Okay, and then there were a couple things we haven't looked at on the Ethernet frame. There's an Ethertype field that's 2 bytes big, and then there's the payload. So Ethertype, not that interesting. We'll look at it later. That's just encoding to tell the next layer up what kind of traffic that is. For example, IP, which we'll cover after the link layer. And then the payload, just remember that everything we talk about from here out, all the layers further up, everything goes in the payload of the Ethernet frame. And that includes ARP, which is the focus of today's lab. ARP also goes in the payload of the Ethernet frame. Okay, so starting the lab, if you open up the file you've got on Canvas, here's a quick intro to get you started. We're just going to walk through that. First, to start a new trace, you see I have a few different options on my VM here for different adapters that I have. I have a couple local area network connections, my loopback, my Ethernet 0, and then adapter for loopback traffic capture. So loopback is capture all the incoming and outgoing traffic, capture that coming back to your system. I think you can use that if you prefer, but I like using the one that I'm actually using for internet. So in this case, this computer is connected by its Ethernet port. That's where all the traffic's coming in. You can see the little spiky doodads indicate that you're getting traffic packets and whatnot. If you are on Wi-Fi, that might be your Wi-Fi instead. So just try to figure out which device, which adapter you're connected with, and click that one to start the trace. So if I double click it, the trace is started. There's a buttload of traffic coming through. Traffic comes very, very fast. Of course, there's going to be lots and lots of packets coming at any given point. Packets are small, and you have to send a lot of them for all the different network things that we have. Okay, to stop the trace, so stop collecting traffic, stop getting packets from that interface, you would hit this red square here. So once you've got what you need in this class, once you've got what you're looking for, you should hit the red square so you don't just have a gigantic trace of a billion packets. It can also start to get slow once you've collected a certain amount. And if you want to start over your trace, you would hit that little fin with the recycling type symbol next to the red square. And for this class, I don't think we'll have to save any traces. I'm not going to require you to submit any traces to me, so you can always say quit without saving when it asks you, or continue without saving, unless you have some compelling reason you want to save your trace. So there, I just started over. Alright, now divert your attention to the filter at the top. This is the heart of Wireshark, the ability to filter all of these tremendous quantities of packets by your desire of what you want to see. So in this case, if I can filter by ARP, and notice when I start typing, all the different kinds of filter options appear, and there are a great deal of them. You can filter traffic by anything you've ever wanted, anything you've ever wished for. So I'm just going to do ARP, and then I'm going to press enter. Remember to always press enter when you're finished applying your filter. Even if you remove your filter, if you want to go back to seeing all the traffic, you need to press enter for it to update. So I'm going to go back to ARP and just sit in that for a bit. Hopefully these VMs give us the ARP traffic that we need to finish. Also, remember you can use the standard ampersand, ampersand, and vertical line operators as and or in your filter up there. So if you want different criteria like ARP and from a certain address or that sort of thing, you can do that with the ampersands and the vertical bars. So each of the lines that we see here is a packet. Alright, so if we click on any of these, if we click on whatever we find here, you can also use the arrow keys to move up and down, so don't think you've got to use the mouse. The arrow keys are very useful in Wireshark. So if we've selected any packet, let's look at this one. And I'll go back to the description here for a second. We'll see some drop-downs, also pictured in the description here. This one has more drop-downs because it's a packet from a layer further up. So let me pick a packet from a layer further up. See, this one has more drop-down options. I have frame, Ethernet, Internet Protocol, Transmission Control Protocol, and Transport Layer Securities. Each of these roughly correspond to one of the different layers of the OSI model that we're looking at. So we've looked at physical and we've looked at data link, the link layer so far. So we can open up our frame here to see information about the physical layer info, time shift, epoch time, delta from previous captured frame, all that good stuff that most people generally aren't interested in, but some people are, and it's available there for you, different time info. So remember, you don't get a lot of the physical layer info in Wireshark because it doesn't get to the operating system. So we don't see that CRC checksum, and we don't see the preamble here, right? Those things happen on the physical layer, and they don't make it up this far, so we can't even see those here. But we assume that if something's here, it passed the CRC, and it probably had a preamble at some point. Alright, so if we want to look at the link layer stuff, that's going to be the second drop-down, the one that's called Ethernet 2. Here we see all the things that we've learned about so far. We see the destination MAC, the source MAC, and then we see that type field that I just talked about. There's 2 bytes to tell you what kind of traffic it is on the next layer up. In this case, it's IPv4. Alright, and do remember that everything in the further drop-downs, so everything in Internet Protocol version 4 and up, all fits into the payload of the Ethernet frame. So what you're seeing here are payloads stuffed into the headers of other further down layers. So this is the first layer we're looking at. Everything beyond here will be stuffed into the payload. Also notice that if you select, for example, destination, see this large box down here on the bottom. So over on the left you have the view of your packet in raw bytes. So packets are transmitted as bytes. That's one of the reasons that the second homework requires you to convert things to UTF-8 and 16 and 32 to get you a feel for how converting things to bytes works, because everything gets transmitted as bytes. And if we see here the destination is B8, 38, 61, 70, 62, 40, that corresponds exactly with the first 6 bytes of the raw packet itself. So the destination is just the first thing in a packet. And if we click on Internet Protocol version 4, we'll see that the header spans from there to there. The transmission protocol header spans from where the blue selected is there. And the transmission layer security, the final payload of this actual packet, spans the remainder. So we look at it and we see actually most of this packet is overhead. About half of the packet is lost to overhead. But yeah, remember, you can always see the raw bytes, and you can also see the converted, I believe this is UTF-8 interpretation of those bytes. So if we can find a packet that's not encrypted, something like this, you can see HTML junk showing up in there. So field, div, body. So it's trying to convert those bytes into text, and you can sometimes see the text of traffic that way. Again, those are the contents of the packets. Okay, so we see all kinds of fun HTML stuff. Alright, let's get started with the lab itself, so just follow along. If you're having problems with your Wireshark setup or whatever, come to office hours and I'll help you out. For this lab, you can turn it in anytime before Wednesday evening, and it's fine. You don't have to follow along with me today. That might not be the case for the future ones, but for this lab, it's fine. So I'm going to zoom in a little more so this is more visible. That should be good. Let me know if that's not good for anybody. I don't want to cut off too much of the Wireshark window. So first, what we learned about in class is technically what's called the RFC 894, the Ethernet Type 2 frame. And this is not actually synonymous with link layer, so there are other kinds of link layer protocols. It just happens to be that it's extremely dominant. We'll see the same thing for IP on the next layer up. Essentially, all traffic goes over the Ethernet Type 2 frame. And it's good that it's dominant, because otherwise our network adapters, our NICs, would have to support multiple different kinds of link layer traffic. It's nice that everybody in the world just essentially has to support this one and a couple of others. But let's see if you can scan through your trace and find something that's not Ethernet Type 2. So notice it says Ethernet Type 2 in the link layer description there. Let me go back to my big one here. And notice how there was a little lag there. It's because I've been running this trace too long. I'm going to stop it. I think this is enough traffic, hopefully, for me to find something. And I'm going to hunt, and I'm going to try to find something that's not Ethernet Type 2. This is a very hard task. You probably won't be able to do it. If you're on Wi-Fi, it's almost certain you won't be able to do it. Different colors correspond to different kinds of packets, so I know all the purple ones are going to be Ethernet Type 2, because those are all TLS over TCP, which we'll learn about later. But all the purples are going to be the same. All the blues are going to be the same as all the other blues. So none of those are going to be anything different. Let's try to find a fancy color. Oh, I saw some funny green down there. Maybe that'll do the trick. Oh, here's a SSDP. Nope, that's going to be Ethernet Type 2 as well. Here's a browser host and out. No, that's Ethernet Type 2. So this is a hard game to satisfy. It's unlikely you'll be able to do it. So I posted an example there. You can also try to search, there's a couple common protocols that I listed there that don't follow Ethernet Type 2. So let's see if I have any of those. EDP or STP. So if I want to do both of those, I would do EDP or STP. And I don't have any of those, so I'm not going to be able to do that. Back to the regular trace. So yeah, I failed in my adventure here. I'm not able to find anything that's not Ethernet Type 2. So you'll notice in these hundreds of thousands of packets, or however many I've traced here, it's definitely quite a few. You can scroll forever. I don't have a single one that was transmitted over something other than Ethernet Type 2. So let's go back to the example that I did provide that I found on John Carroll's network a while ago. It's something called the IEEE 802.3 Ethernet packet. Okay, and it's called logical link control is what its payload is called. And the question being asked for you is, what makes this packet, or the one that you found, if you did find one that wasn't Ethernet type 2. And if you did, by the way, take a little snip and post it to Discord for everybody else, because it's pretty tough to find one. So congratulations if you did that. So what makes this packet, or the one you found, different from a traditional Ethernet 2 frame? You might have to look this up. We're not going to look it up here, but I'll spoil it for you. It has a different header. Okay, and I'll let you look up on your own what's different about the header and why might they have changed the header slightly. So it has a different header. That's about it. It has a slightly different payload as a result. But why might they have altered the header for that? Someone asked, I have a black with green text. Is that Ethernet type 2? I don't know. Click it and see. If it still says Ethernet 2 here, then it's still Ethernet 2, just like all of these say Ethernet 2. You'll notice that they all are also Internet Protocol version 4. Also, again, a pretty dominant technology, but that's one that actually at least has one competitor, in fact. But Ethernet, basically all link layer traffic goes over Ethernet, so you'd be very hard-pressed to find something that doesn't say Ethernet 2 right there. We got nothing. Black generally, by the way, things with a black background are either lost or retransmitted packets. So it's something that failed to arrive and had to be retransmitted, or arrived damaged or something of that nature. We'll look at retransmissions on layers above more, but that's what the spooky black background means. All right, so we'll move on to the next thing. Now filter your traffic by ARP. So type ARP in your filter bar and press enter. If you're on your home network, you might not have too many ARPs going around. One way to force an ARP to happen is to take another device on your home network. So if your phone's connected to your Wi-Fi, for example, just turn off your phone's Wi-Fi and turn it back on again, and it will ARP for something. We'll talk about what when it first reconnects to your home network. Okay, otherwise I just have these ARPs here. If you're on Wi-Fi, you will probably see a lot more announcements than this, and they'll be called either gratuitous ARP or announcement, depending on your version of Wireshark. So I don't have too many messages here, and all that trace, it looks like I only got something like 20. So let's look at what the question asks me. Filter your traffic by ARP and post a snip of any ARP request that was sent as a broadcast. So let's look at the destination field here. All of these here match that criteria. Their destination is broadcast. Okay, so let's expand it so that I can see the whole message here. You have bigger font or smaller font than me, so you could probably capture this whole thing. But what I want you to do is just try to get the body of the message in there as well if you can. Maybe get your field smaller there and just kind of capture that whole thing and post that into your lab. Just show me that you were able to find a thing that had its destination as broadcast. So again, if we look at the details of that Ethernet frame, we see that broadcast FFFFFFF was the destination here. Okay. And again, if you're having trouble generating a broadcast, just turn off your phone's Wi-Fi and reconnect it, or do that with some other device on your network. This is a lab that's much easier to do in the classroom because everybody connecting to the computers triggers an ARP. I don't think it's the same for the VMs. Next question, do you get mostly ARP requests, ARP replies, or equal proportions of both? Why is that? So let's look at what I got. Let's look at how we can tell if it's a request or not. All right, so let me ask you to look through the body of the packet, look through your Ethernet header, look through the payload of the ARP packet. Try to figure out, how do you know if it's a request or a reply? And just answer that in Discord or live chat. How do you know if it's a request or a reply? It's pretty easy. Spoiler. How do you know if an ARP packet is a request or a reply? You might notice there are other options besides request and reply too. You know if it's a request or a reply. Where do I see it? Someone said it's under address resolution protocol. Well, yeah, it's going to be there somewhere. Where is it? What's the field called that tells you if it's a request or a reply? Sounds like some people aren't having a good time with Wireshark. Now remember, when you expand this box, it's showing you all the fields, all the different elements of the header. So like when you expand the Ethernet 2 box, you're seeing what we learned about in that header, the destination, the source, and then the type. Those are all different things that pack into this header that we learned about. Destination, source, and type are just the first 6 bytes, the next 6 bytes, and then the next 2 bytes, and then followed by the payload, in this case, ARP, right? And the checksum that we don't see because it's on the physical layer. Someone said opcode. Yes, it's the opcode. If you look into the ARP payload, you'll find the opcode down here. It's also an important piece of information, so Wireshark has put it right up at the top, so you don't even need to expand the box to see if... Oh, all right. That's an inconvenient place for that to be. Let's just move this a little. Okay. You don't even need to expand the box to see that it's a reply. It says it right in the drop-down for the payload because it's an important piece of info. So you can look at the opcode, or you can look up there. Now let's see, how long is the opcode in bytes? How many bytes is the opcode in the ARP payload? How many bytes? And for bonus points, meaningless bonus points, how many possible opcodes can there be, given that we're using that many bytes? How many bytes is the opcode? Remember, you got to look down in the raw bytes of the packet further down. We can see that the opcode for a reply is 2. The opcode for a request is 1. How many bytes is the opcode? And for bonus points, how many possible opcodes can there be? How many bytes is the opcode? And how many possible opcodes can there be? There's no points off for wrong answers, guys. Just fire away. You know, pew pew. Doesn't matter if you're wrong. The faster you're wrong, the faster we finish. The less you reply, the less we get through today, and the more you have to do on your own. So how many bytes is the opcode? How many total opcodes can there be? That's a big number. All right, let me check if that's correct. Why don't you post the formula you did to get that? And how many bytes is the opcode? It's 2 bytes. 2 bytes, right? So we see if we click on opcode, we see 2 bytes get highlighted, 0, 0, and 1, or 0, 0, and 0, 1. 0, 1 is 1. So the request is type 1. That's a pretty simple decoding. If we look at a reply, 0, 0, 0, 2. Again, you got to click here and see it get highlighted in blue. So that's 2 bytes. A byte is 8 bits. 8 bits. So that gives us 16 bits total of information. So 2 to the 16th opcodes. So a little smaller than the number that Optics gives in chat. That's going to be, 65,000 or something around those lines. Yeah, so 2 to the 16th possible opcodes. So very ambitious, considering that primarily we only use 2. So they could have probably made this 1 byte without missing out too much. So again, 2 bytes, and you can see them highlighted down there. Okay, so the question asked, do we get mostly requests, replies, or about equal proportions of both? So let me count, and you guys post your results in the chat as well. Do you get mostly requests, replies, or about equal proportions of both? So I've got a bunch of requests, 1 reply, request, 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 reply, request, reply, request, reply, request, reply, request, reply, request, reply, request, reply. So I have way more requests overall. But I have quite a few replies too. So mostly I have requests. Let's see if your results are the same. So if you are on Wi-Fi, your results might be different. So why don't you also post what you're on? So say if you're on Wi-Fi or Ethernet, and then do you get mostly requests or mostly replies? And why do you think that is? Why do you think we mostly get requests? This goes back to how ARP works. Remember, when you want to know somebody's IP address, who do you send your request to? You send it to broadcast, right? So everybody gets the requests. Everybody gets the requests. But the replies, only the intended audience sends back a reply, right? So everybody gets a request, but only the person who has that address and who answers it, and the person who asked for the request in the first place will see the reply. So you're going to have a lot of requests for addresses that aren't yours, that you would ignore, and then you would have a few replies for requests that either you made or requests for your address by somebody else that you've replied to. So that's why the proportion is more requests than replies, because you see everybody's requests, but only replies that are relevant to you. And obviously you're going to see a lot more requests if you're on a network that has more than 2 machines. If you only have 2 machines on your network, one of them probably being your router, then you would probably have an equal proportion. On a Wi-Fi, you see tons of requests usually for different devices, and you also see a lot of announcements. Okay, so when making a request, what goes in the target MAC address field? So in the payload, remember when we're asking for an address, we're asking for, let me go to request here, for example, who has 143.105.164.1, and then tell, and then your own address. Okay, so who has that? Tell me. So what do we put in the target MAC address when we're making this type of request? I will also point out a different one. Here's the target MAC address here. Okay. I'll also point out a different one. This. Our target MAC address is zeros, and this is a request. So there are actually two kinds of requests in terms of what goes in the target MAC address. What is the difference between these? What's up with that? How come this one asks for, it's got a bunch of zeros, and this one's got an actual MAC there already? Let's think about what ARP is for a second. So we have an IP address, our own address. That's the tell me part. That's our own IP. And then we have an IP address where we want to map it to a MAC. So we know that there's, or we think that there's somebody at a particular IP address. We want to know what their physical address is. So we send a broadcast to everybody on our physical medium in order to ask for their MAC. So if we are asking for the MAC of 143.105.1.641, how come there's already something here? Presumably we don't know it. So how have we already populated this field in our request? These are what you would expect, the 0000. We don't know the MAC address of the recipient. So these are what we would expect in a request. And this is what you will see, by the way, these 000 ones. You will see if you disconnect and reconnect your device, like if you did it with your phone to trigger a broadcast, like I said, then you would see one of these. This is when you don't know a target's MAC address. This is a conventional ARP request. Who has a particular IP, and you leave the target field blank, and then when they send their reply, they will reply with the actual MAC that they have. They will reply to you. So we don't see the reply here because we don't own 143.105.1.641. So we wouldn't reply to this message, we just see it. These messages here, what are these requests for then? What's the purpose of these requests that already have the MAC in there? Well, the entries in the ARP table, remember, don't last forever. They last at most a few hours. Sometimes they're configured to last just minutes, right? So what might these messages be for, given that the entries in the ARP table don't last forever? What might the ones with the MAC already filled in be for, given that the entries don't last forever, versus the conventional request for a MAC that is left as zeros? The answer to this question, by the way, is that it's all zeros, 0000000. If you're making a request for a MAC you don't know, or an IP you don't know. Someone said to make sure it's still the same or to check again. Yes, essentially that's what the purpose of these kinds of requests is. If the entry in your table is about to expire, so you are supposed to just delete it from the table when it expires, you would send one of these kinds of requests to refresh it. And so at that point you already know their MAC and you're making sure, so you're just sending what you already have in your table, and in this case they would answer. And notice that this pair of requests here, the target was B8, 38, 61, 70, 62, 40, and the reply is the same, so that MAC hasn't changed. So we're looking at the same IP, their MAC hasn't changed. That's 165.12. They're asking who's at 164.1, and 164.1 replies that it is still at that same MAC. So the two kinds of targets there are a target that you don't know, which is an all-zero target, or a target that you're trying to refresh, which should be the last MAC that you have for them, which if you'll think about it carefully, you'll know is unnecessary, because even if you had left that target field blank, they would still reply with their MAC address. So you actually could leave that blank. I think it's up to whoever implements the ARP protocol to decide if they want to populate that target or just leave it as 0. So that might even vary between your different computers. You might see different ARP implementations where all the requests are all zeros. That would be perfectly fine. So what company is the manufacturer portion of your Mac registered to? It's tough to determine which one is yours, but it's probably one of the ones where the request originates and it's not to broadcast. That would be a good way to figure out which one's yours. We'll look into how to figure out which one's yours more later. The other way you can do it is to look at just all the traffic and see which device most of the Ethernet traffic comes from. So mine's all coming from Cisco 70 for the most part. And talking to VMware B5. Cisco 70, probably not my VMware machine, so I know I'm on VMware here, so I'm probably the VMware one, and Cisco is probably the router servicing this connection. So I'm going to assume that I am this VMware B5 one. All right, so to see my manufacturer's address, first I need to find that link. I'm just going to copy it for safety, guys. Don't enable links in your PDF. That's a bad idea. Alright, so I'm going to copy it for fun. Go here, and then let's find, how do you find your manufacturer portion of your Mac? Well, that's going to be the first 3 bytes, right? The manufacturer portion of your Mac. So mine is B5, 7B, 7A. And these are formatted with dashes between them instead of colons. So I want to look for, they also use uppercase as if it's case sensitive. So B5, 7B, 7A. Let's see if I find it. Oh, whoops. Read the bytes wrong. The bytes are over here. That's 005056, also there as well. 005056. I read that. It's probably part of the device's name. So 005056 is what I'm looking for. 0050 dashes. Do, do, do. 005056. How come I can't search this thing? There we go. Finally made it. Sometimes it takes a while for that page to load. Obviously, I just clicked that link, so it must still work. Hopefully you don't get a 404. And that's registered to VMware Inc. Notice VMware Inc. has a couple in proximity here, a couple of bytes in proximity here. They don't need that many because every network of VMs can have their own MACs. They can have not unique MACs because they're going to be in a cluster of VMs only with other VMs. So this is one of those rare situations where the MACs don't need to be super globally unique. But the question asks, what is their address? Actually, that's kind of ambiguous. I meant their physical address. So VMware Inc. is located at 3401 Hillview Avenue in Palo Alto, California. So if yours is also there. There you go. 3401 Hillview Avenue, Palo Alto, California. You might find, if you're using your own machine, a Chinese company like Huawei or Shenzhen or whatever. If it's a Netgear, that's probably your router. Someone asked in chat if you should put in your Netgear. If it's Netgear, it's probably your router, since Netgear is primarily a router manufacturer. You could have a Netgear NIC in your machine, but it's probably the other one then. It's probably the one that one's talking to. For this question, it doesn't matter which of the Macs you've determined is yours. If you got that wrong, it's fine. Just one of the Macs you think is probably yours. Alright, you might have noticed one of these, so I didn't have one on my trace here. Maybe I'll start again and see if I can get one. A gratuitous ARP, or an announcement. So you might have noticed one of these. It's called announcement in newer versions of Wireshark. So if you just installed Wireshark on your own machine, it'll be called announcement. Instead, if you're using the John Carroll VM, then it will still be on the older version, and it will be called a gratuitous ARP. Why is this a gratuitous ARP, or an announcement? What is that? You'll notice there's a special edition in Wireshark. It's not part of the payload, but Wireshark adds this is gratuitous true to the description in the payload. That lets you know that it's a gratuitous ARP or announcement. So what is this? When might a machine decide to send one of these? What's up with this thing in general? What is a gratuitous ARP? Let's see if I can get one. So since I have no control over other machines on the VM, I can't force a gratuitous ARP here, unfortunately. So if you're on the VM, you might just have to use my example here. But if you trace for long enough, you will see one eventually. What is a gratuitous ARP? Some of you probably found out that your network device is manufactured by someone different from the type of computer you have. So whether you have an Apple or a Dell or whatever the manufacturer of your machine is, your network card was probably made by either a Chinese company or something like Intel or Qualcomm or Broadcom, Realtek. One of those companies probably made your network interface cards. So some of you probably, when looking up the Mac, found those kinds of manufacturer IDs rather than the manufacturer of your full machine, your computer, which you might not have expected. Apple generally makes their own, I think. So if you have a Mac, you probably saw the Mac get registered to Apple. You probably also saw that Apple has a ton of different things to its name. Let's see how many Apple has. I think trying to do things on the internet while I have the VM open is a bad idea. You know, maybe if you're working with this file, it's better to just download it as a .txt file and search it that way. If you're having trouble with it, you just download it and open it in Notepad and search it that way. So anybody have an answer to the gratuitous ARP question? Here's an ARP announcement. I finally got one. Is gratuitous true? Is announcement true? Also got some probes here. Those aren't in the lab, but I'll give those an honorable mention. So is gratuitous true? Is announcement true? It's a broadcast. What is a gratuitous ARP? You'll notice that the target is zeros. In my example here as well, the target was broadcast. So this is a difference in how the standards are implemented. It doesn't actually matter. The destination on this one is still broadcast, though, right? Okay, so on this one it's a little bit clearer because the destination and the target are both broadcast. This implementation here, where the target's set to 0 but the destination is set to F's, can be a bit of a confusing implementation, but doesn't matter. So these gratuitous ARPs, these announcements, are always sent to broadcast. See if I can find one where it's all F's instead. Nope. Mine are all zeros for the target. All right, so I haven't got an answer yet, so I'll just answer it. What is a gratuitous ARP and or announcement? Slightly different in some people's estimation. Some people say they're the same thing. This is one of those things where Wireshark updated what it called it because most people think gratuitous ARP is an announcement. And gratuitous is a weird word. So what does it mean to be gratuitous? It means that you give something when you don't have to. You're extra gracious. And that's what it means here too, is that you basically sent a reply without getting a request. So this is a weird kind of ARP that you might do when you connect to a network for the first time. To avoid everybody having to make a request for you, you just announce who you are. You just send it out. And so it's sent as a request, but it's actually not a request for anything. That's why the field is all zeros. The target IP is yourself. So this comes from 169.254.155.184, and the target is yourself. So you're asking for your own MAC. Well, you already know your own MAC, so you just put zeros or Fs in the field or whatever. But everybody else that gets this sees you as the sender and sees your sender MAC. And remember, when you get any kind of broadcast like that, you would add it to your own ARP table. So this allows everybody to add you to their ARP table. So some devices, when they connect to a network, will automatically send a gratuitous ARP. Some devices will also just periodically send a gratuitous ARP so everybody knows who they are. Right? So it's a strange payload, that it's a request rather than a reply. That the target MAC and target IP are basically useless here, so they're filled in depending on the spec of the manufacturer, I guess, or the implementer. The target is always yourself, even though you're not actually asking about yourself. And this is, again, for everybody else to see your sender addresses and update their ARP table according to what they see. So it's a reply without a request having been given. And it again piggybacks on that same request opcode. You would think they would have made an opcode for announcements. I believe at one point they did have a separate opcode for announcements. But so basically ARP operates on two opcodes, but they use 2 whole bytes for them. So the internet has lost trillions of bytes to overhead because they decided to use 1 extra byte when 1 byte would have made do. So if you think about it that way, remember that when you're planning your own kinds of overhead. 1 byte sent a trillion times really adds up, and this byte is pretty much always 00. I think always, to the best of my knowledge, 00. Because there just aren't that many opcodes. Okay, so what is this? It's basically a reply with no request given, sent to everybody. You send it when you first join a network or periodically just to inform everybody. You would definitely send it if your IP address changed. So if your IP address, unlike your MAC, can change, and if your IP address changed, you would send a gratuitous ARP. You would send it if you switched ports on a switch or if you switch connections, but that would be the same as joining a network because your cable would be unplugged and plugged back in. So that's the same as joining fresh. And then again, you might send it periodically to update everybody's ARP table. Let's say you know that ARP table entries expire every 2 hours or something on your local area network. Rather than making everybody send a reply every 2 hours, you would send a gratuitous ARP, let's say at the 1.5 hour mark, and that allows everybody to refresh their ARP table. You might also see several ARP requests sent to a specific device not broadcast. So we did see a few of these already. What are these? Why are they sent out? You typically catch more of these on Wi-Fi because you'll catch the ones that are not for you. So you'll catch the replies for other devices on the Wi-Fi sometimes. So you'll catch the replies that were not intended for you. That can get confusing. It's less confusing on LAN. You only see the replies directed at you. So what are these individually sent ones? Let me find one here. Here's some that are individually addressed. So this is VMware, or Cisco, which is probably the router servicing this connection, asking VMware Let me go to the request first. Sorry, I was looking at the reply. This is VMware asking Cisco who has 143.105.164.1, and Cisco replying, still me, bud. Still me. So I guess, again, that's one of those refreshers. Who has it? Still me. And then immediately after, hey, who's got that? Still me. Hey, who's got that? Still me. You could send a few just to make sure that you get a reply. These are sent just like 30 seconds apart, I think. So, a very spammy network here. Well, that's all the time we have for today, so the remaining 3 questions are going to be homework, but feel free to come to me during office hours or ask in Discord if you're having trouble answering one of these. So I hope you guys were able to complete this lab for the most part. And I will... Oh, and the homework is due Wednesday as well, so don't forget that too. And I will see you guys on Wednesday.